Space exploration presents major challenges, among which propulsion stands out as really significant. The distances involved are vast, and few constraints make traveling directly to distant planets impractical or even impossible. This is precisely why scientists and engineers have turned toward a remarkably clever technique known as gravity assists. Gravity assists allow spacecrafts to leverage planetary motion. Spacecrafts are gaining or losing energy by interacting gravitationally with planets. This technique has profoundly expanded humanity's ability to explore deep space, enabling missions like Voyage's journey across the solar system. In this video, we will first explore the key ideas behind gravity assists. We will also see how spacecrafts can gain extra speed by firing engines at specific points, discuss some surprising ways gravity assists can be used, and look at famous missions that took advantage of this method. At its core, a gravity assist or planetary flyby is a maneuver where a spacecraft approaches a planet and uses its gravity to alter its trajectory and speed. The spacecraft doesn't fire its engines. It simply falls into the planet's gravity well and swings around it, exiting on a new path. From the planet's perspective or reference frame, nothing unusual has happened. The spacecraft enters and leaves with the same speed, just in a different direction. But to an outside observer, for example one watching from Sun's frame of reference, the spacecraft has either sped up or slowed down. And that difference is key. This works because planets are not stationary. They orbit the Sun at high speeds. For example, Mars orbits the Sun with 24,000 kilometers per second. When a spacecraft approaches a planet, some of the velocity of the planet is basically transferred to the spacecraft. The planet in turn loses a small fraction of its momentum, but because the planet is so massive, the effect can be neglected. Within the planet's own reference frame, there's no net energy transfer. The spacecraft gains no speed relative to the planet. The energy is conserved. But within the solar reference frame, energy is indeed transferred from the planet's motion/velocity around the Sun to the spacecraft. This transfer is entirely consistent with the laws of physics. It's not a loophole or a trick. It's simply a careful exploitation of the high speeds at which planets orbit the Sun. And it's this interaction between the spacecraft and the planet that allows missions to travel far beyond what fuel alone would permit. Now that we've covered the basic idea, let's look at the concept that makes gravity assists even more efficient. There's a principle in orbital mechanics that often feels counterintuitive. If you want to get the most energy from your rocket burn, you should do it where you're moving fastest, not slowest. This is known as the Oberth Effect. The reason for this lies in the kinetic energy. The energy of motion increases with the square of velocity. It is a quadratic function. That means if you add a bit of speed when you are already moving quickly, the energy gain is significantly higher than if you added that same amount of speed while moving slowly. So when a spacecraft is at its closest point to a planet during a gravity assist, it's traveling at its highest speed. Burning fuel at that moment results in a far greater increase in kinetic energy than the same burn would provide further out. This is why missions perform engine burns during planetary flybys. The spacecraft uses the planet's gravity to accelerate, then fires its engines at that high speed point to get even more out of the maneuver. It's an efficient combination, gravity assists plus propulsion, scheduled to take full advantage of the Oberth Effect. I think this concept is really cool, because it's a direct physical phenomenon, which one can take advantage of, and the connection between the formula, the v squared, and the implication in reality is really simple and understandable. Here's a simple everyday example how you can use it/see it. When you are riding a bike downhill, say down a ramp, slope or incline, you are already moving quickly due to gravity. If you pedal at that moment, your effort adds more kinetic energy than if you applied the same effort while moving slowly on a flat ground, because your speed is higher and energy scales with the square of velocity. So next time, if you are exhausted and are riding a bike downhill and the flat region comes afterwards, keep pedaling, so that in the flat region you don't have to give as much energy. To continue, we will look at a method used to predict and limit the outcomes of gravity assists. One major problem in planning gravity assist maneuvers is that you don't know the exact orbit a spacecraft will have after it made the gravity assist. This is because really small difference in approach, angle or speed can lead to very different outcomes. Here comes Tisserand's Criterion into play. Using this tool, you still can't predict the exact path the spacecraft will take after the flyby, but you can define what types of orbits are even possible. It sets boundaries. In other words, you know what could happen, even if you don't yet know what will happen. The criterion combines elements of the spacecraft's orbit, like its size, shape and tilt, into a single value that stays nearly constant before and after the flyby, when only gravity is acting. This value can then be used to schedule different gravity assists with different planets. A nice visualization is here presented in the graph. This helps mission planners to understand which flybys can lead to viable transfer paths and which options are physically ruled out. Let's now move into a few counterintuitive but important aspects of gravity assists. Cases where the results may seem surprising yet are fully consistent with physics. Not all gravity assists are about speeding up. In fact, they can also be used to slow down a spacecraft. If a spacecraft flies past a planet in the opposite direction of the planet's orbit, it loses energy relative to the Sun, allowing it to drop into a lower solar orbit. Another counterintuitive idea is that you can use inner planets to go further out. It may sound backwards, but by first diving towards the Sun and gaining speed, a spacecraft can use that momentum to slingshot outward on a much larger trajectory. This is possible and often better because inner planets like Venus or Mercury have higher orbital energy and velocity than outer planets, and therefore transfer more velocity to the spacecraft. Finally, each gravity assist can only transfer a limited amount of energy. There's a natural geometric limit to how much momentum can be exchanged in one pass. Typically, only a few % of the planet's relative velocity can be added or subtracted. That's why missions use multiple flybys, even with the same planet, to gradually build up the needed exchange. A clear example is Voyager 2. It used 4 gravity assists at Jupiter, Saturn, Uranus and Neptune to travel across the outer solar system. Without them, its onboard fuel would have only allowed a small fraction of that journey. Using gravity assists, it reached speeds of over 15 km per second relative to the Sun, far more than propulsion alone could provide. That would have been in the range of 3 km per second. These flybys made the grand tour of the outer planets possible with a single launch. To sum up, gravity assists are a practical and proven way to extend the reach of spacecrafts without needing large amounts of fuel. By carefully using a planet's motion and gravity, missions can gain or lose speed, change direction and reach places that would otherwise be out of range. When combined with techniques like the Oberth Effect and guided by tools like the Tisserand Criterion, these maneuvers become even more powerful. They have played a key role in missions like Voyager, and they continue to shape how we explore the solar system today. Thanks for watching and have a look at the videos in the end card. Maybe one of them interests you too.